All right, so before we get more into increasing and decreasing, we are going to make this definition here a critical point or critical value of a function. These will allow us to sort of create those number lines with which we would make those increasing and decreasing sections. So if we think back to our rational and polynomials, those beautiful plus minus number lines, we're going to make those once we have the second definition here, that second bit about how our first derivative is related to our intervals of increasing and decreasing. So critical points or critical values um, are any time that our first derivative is either equal to 0 or undefined. So we could look at these two problems and let's just go ahead and find them. This is something you should be able to do. It's just a little bit of calculus with some algebra on top. So feel free to pause and then try this on your own before you watch me. So for the first one, if we're looking for a critical point or critical value, first thing we need is we need our derivative because we're going to set that equal to 0 or undefined. In this case, we don't really have any great way around this. We we have ahead of us a little bit of low d high, high d low, some quotient. So low times derivative of the top minus high d low all over low low. All right, so there is our beautiful function, our derivative function. We could go ahead and clean this up. We have x plus 2, because we can multiply that 1, minus x all over my x plus 2 squared. This is all equal to 2 over x plus 2 squared, right? Because the x minus x is 0. And so we want to know, when is this thing equal to 0 or undefined? And if we want a fraction to equal 0, we'd need the numerator to equal 0. 2 can never equal 0, so we have no critical values coming from f prime equal to 0. But a fraction is defined when we divide by 0. So we can solve that. We can go ahead and say, well, x plus 2 is equal to 0, means that x is equal to negative 2. That critical point or critical value for that h. And if you think about that, that in terms of the original function is our vertical asymptote. So it makes sense that our derivative would be undefined there, because in order for our function to be differentiable, we need continuity, and we don't have continuity at an infinite discontinuity such as a vertical asymptote. All right, example 2. Now they have given us a first derivative. Thank you so much. We're not going to have to do that work. And we need to figure out what the critical point is. So we are again saying, okay, when is this equal to 0 or undefined? Now, let's just think about undefined for a second. There's two different things happening here. We have a cute little cubic multiplied by a cute little exponential. Cubics, they have a domain of all real numbers, right? Nothing is going to cause me trouble to subtract 1 and cube. That's fine. And exponentials also have a domain of all real numbers. So when we multiply these two together, we have this product of functions. Our domain remains all real numbers. So we don't have to worry about the undefined situation here. This will never happen. But we do need to say, when is this equal to 0? And to solve that, we would probably use that zero factor property. We have two, like I said, a product of two different functions. And we'd go, okay, well, if either of those things is 0, we have an issue. So we'd be two different equations. X1 cubed is equal to 0, which we know doesn't really need the cube there, because you cube root both sides. That's whenever x minus 1 is 0. So we have a critical value at equal to 1. And we could also set up the to the 2x is equal to 0. And we might scratch our heads at this for a second, but we have two ways to recognize that there are no x's where this is going to be the case. One is realizing our exponential has a horizontal asymptote at y is equal to 0. It never hits 0, right? It never crosses that axis unless, of course, we have a shift downward. The other way is to just not realize that about our exponential functions and try to solve this. So we'd probably take the natural log of both sides, and then we'd get 2x is equal to whatever the ln of 0 is, right? And go to type that into a calculator and realize that there is no such thing as ln of 0. This is undefined, so that does not work. So we have only one critical value for example 2, and that's x is equal to 1. And so what it is we're solving when we solve these questions is we're trying to find, in terms of our critical points, we're trying to figure out all of these values where we could possibly be changing from increasing to decreasing, right? Undefined is something like those two corners, right? Those are not smooth, so they wouldn't be differentiable. And then something like our little tiny, our vertex there, we switch from decreasing to increasing on that parabola looking part of this graph, that would have a slope of 0. That would be when our first derivative is 0. So when we're solving for these critical points, what we're finding is all of these places where potentially our graph could have changed from increasing to decreasing or vice versa.